Okay, let's have a look at some power modeling then. Good news is the work that we were doing yesterday in school was all types of power modeling. So we were doing direct and inverse proportion. We were looking at the proportion of two variables where one might be squared, where one might be cubed, where we had inverse proportion, and that's all types of power modeling. So please don't worry about the word modeling. It's nothing to do with paper 6 in this instance, but the modeling idea of finding something that's going to fit with some behavior is kind of implicit within that word modeling, and we'll have a look at exactly what that means. So essentially, when we've got a power model, what we're looking at, and you can see this idea here, that we have, if I underline this, y equals something x to another power. Now, obviously, that's going to react differently when we have different values of b. So we defined it yesterday as being proportional or inverse proportion, and we can say that if b is greater than 0, then we have direct proportion, or sometimes it's called variation, so I might use variation. And then also, if b is less than 0, it's negative, then we had inverse proportion, didn't we? And we have a good understanding of our indices to think, well, if we know that if b is negative, if this b is negative, then that's going to make it a over x to the power of whatever that negative b thing was. And so then we can see, hopefully, that that's going to be some sort of direct or inverse. Oh, I've used variation and proportion. That's interesting. Let's be consistent. Inverse variation. Oops, I can't erase it anymore. Variation. Okay, now what happened yesterday was we were looking at numbers that fit exactly to what we were trying to do. But in the example that I've got here below, there's not going to be an exact formula for the variation, the proportion. So all we're going to do is we're going to use our GDC in order to help us find the best fit of a relationship between the d centimeters and the force newtons. So let's just have a little read of this. We've got gravity is the force of attraction which exists between any two objects in the universe. Force of attraction F newtons between two masses d centimeters apart is given in the following table. Marvelous. Okay. Graph F against D and show that the power model is reasonable. Okay. Power model, it tells us in the question, there's a key word, power model. So we're going to have to use our GDC in order to do this. So we're going to have a new document and we're going to put in a spreadsheet. Always worth labeling what we're dealing with. And D is a measure of the distance. And then we've got force is our newtons. So if I go through this, 24, 26, 28, 30, 32. Oh, this is going up there, nice. Oh, I've got that wrong. 36, 38, and finally 40. Okay, let's just double check what we've got on the other side then. I'm going to have to be a bit more careful on these. 237, 202, 174, 152, 133, 118, 105, 95, and 95. Okay. Now, just like way back when we did our Usain Bolt, we're going to hit Document and we're going to insert Data and Statistics. So now we're able to plot the data that we've got. Now along the x-axis we want our independent variable, which is going to be our distance, and on the y-axis we're looking for force. Okay, so this is now us answering question A. We've graphed F against D to show that the power model is reasonable. Well, it looks like it's kind of following a curve downwards. It looks like exponential decay, like especially with this down the end. It's not really fitting a linear curve. So that's what we're looking for to answer that part A there. So let's go on to B. And B says to obtain the power model which best fits this data. Okay, so A, I'm going to write that I've graphed on the GDC, and I might choose to see if I can insert that if I was working on a Google Doc, perhaps make a screenshot of that. But what we're interested really is being able to do this part B. So if I go back now to this data, and I'm going to look to do a power regression. Just like the linear regression and quadratic regressions we've done before, process is the same. So menu, first of all, statistics, stat calculations, and we're going to scroll all the way down here to a power regression. Marvelous. Now my X list was my distance, my Y is my force, and that's usually the order that things come in over here, X and Y, but we also talked about independent dependent variables, so hopefully we're getting these the right way around. And it's going to give me my first result in column D. That's not really an issue. Maybe I'll just shift it across to C, so it's next to, so I've got quite a small screen here. And here we are. So we've done the power regression. This tells us the format that our regression line is in, so it's something x to another power, where that first thing is A, and that's this number. So I'm going to write that as 95869. 0.8, we might as well be accurate, times by x to the power of b, which is negative 1.89416. Okay, and there we are, that's B done. So I suppose we could say, if we wanted to rearrange that, because we've got that negative power, let me just zoom in so I can be a bit more accurate with what I'm writing. So that is equal to, yeah, I'll change from an or, just to write an equal sign. So that is equal to 95869.8 over x to the power of 1.8914. Oh no, there's not a 1 there. This is why I should do it neat. Four, 1, 6. Okay, part C then is asking us what factor confirms that the fit is excellent. For this, we're going to look at the R² value, and if it's close to 1, then it's a really good fit. I mean, this couldn't be much closer, so we're saying C R² is equal to 0.991, which implies it's a really good fit. Okay, part D, and this is always going to come up. You're going to now have to use your power model to find out something. So now I'm actually going to just adjust what I've put previously. I've just remembered that we're in terms of f and d, and I've just written down x's here. So what I might do is I might just imply that what we've found here is that actually our f is roughly equal to and that shouldn't be an x, that should be a d in this context. Okay, now that is what we're going to use here, this thing here. So let me just highlight that. That's what we're going to refer to. Let's have a little look. So now that makes this a little bit easier. So estimate the force. Now we're just going to plug in D for uh, 20. So F is roughly equal to what have we got? 95869 over 20 to the power of 1.8 9416, and so that comes out as an answer of, I have to do this, I'll insert a calculator, and we're dealing with, let's set up the fraction, sometimes easier to see it that way, 95869 over 20 to the power of 1.89416, which gives us an answer of 329. Does that kind of make sense? Well, it kind of does, yeah. So we're getting a value here that's smaller than this, and we're getting a value here that's bigger than any of these, and that kind of seems to be the trend. So I can have a little bit of confidence in my answer. So that equals 329. Next, 29 centimeters apart. Now this is going to be quite a good one, a much better one, because now we're interpolating and we're going within our data, so it's much more reliable. So here we're going to then do same calculation, 95869 over now 19. Was it 19? Sorry, no, it wasn't. It was 29 over 29 to the power of 1.89416. This should be quite quick for me because I can copy and paste. You can do this on your handheld GDC, worth looking that up if you've not done it before. So now instead of 20, I've got 29, and I get 162, which is between these two values and is between these two values. So I feel really confident that my model is correct. I'm getting something that I should be getting out of this. So that equals 162.8. I'm going to round it 3 significant figures, so 163. And then finally, for 50 meters apart, oh gosh, right. For 50 meters apart, that's going to be 500 centimeters. No, there's 100 centimeters in a meter, so that would be 5,000 centimeters apart. Okay, so now, for not very clear here, 1, 2, and 3, I'm going to do 5,000, sorry, 95869 over 5,000 to the power of 1.89416. Okay, so what have we used here? We've used a really big distance up here, which means this is getting smaller and smaller, kind of makes sense. And I'm getting a force of 0.00945. So 0.00945 if I round that to 3 significant figures. And there we are. That's how it works. So what I'm going to ask you to do is to scroll down on your Google Doc. I've put some questions for you to have a go at, put some solutions, and if you can get that done at some point today and then submit your answers, that would be great. And that's us done. Thank you for tuning in.